Hello everyone, today in this video we'll be discussing the module 2 of cloud computing BCS601, and in this video we have the topics. The 5 topics are the main 5 topics. I'll be telling you what all you need to know from the exam point of view to score more than 80% marks. Make sure you watch the video till the end and don't miss any of these topics. And if you have any doubt, you can ping me on Instagram here. And before starting, please do like and subscribe. It helps me make more videos like this. So without wasting more time, let's get started. The first topic is implementation levels of virtualization. Okay, so in this module we will be learning what is virtualization. Okay, virtualization means what? That which is not present in reality. Okay, so the physical system which is present, your computer is there. Okay, that is a physical system. But if that computer's data is taken and put it into a different system, okay, like using a Wi-Fi, okay, so you'll be able to access this system which is not physically present at that point. That is called as virtual environment. Okay, so here what we'll be learning is how does virtualization work and what are the different aspects of it. Okay, so I'll be telling you what all you need to know from the exam point of view. Okay, so implementation levels of virtualization, that's the first topic. Okay, before that let's discuss the definition of virtualization. Virtualization is the process of creating virtual instances of computing resources in a single physical machine. Okay, what we are creating? The virtual instances of computing resources. To run a computer, what all is required? Network is required, right? And the storage is required to store the data. Okay, and another thing is the RAM required to process the data, and you need a CPU to do the arithmetic calculations. All those things are required to run a system. Okay, and what we are doing is we are taking all of those systems and we are making a new system, okay, virtually. Okay, sending this data over the network so that it will be accessed elsewhere in the world, and that will be running. Okay, that is called as virtualization. Instead of a physical machine, we'll be accessing it virtually. Okay, so what is the difference between the traditional computer which we all have and a virtualized computer? Okay, in the traditional computer it is dedicated to single OS, like it is either Windows or Linux or Unix or Mac or any other Ubuntu or whatever it is. Okay, so it is a single OS will be there in the traditional computer. But in virtualized computer you have multiple virtual instances. Why it is so is because we are getting the instances from the internet. Okay, we are getting the instances from the internet, so multiple instances can be stored in a single computer and they can be accessed whenever required. So you can access this when I want, access this when I want, access this when I want. Okay, so that's why a virtualized computer will support multiple resources. But a traditional computer will be having a hardware. Inside that hardware only one operating system is supported, and that is installed. So in the real computer only that operating system will be the single operating system. Second is run one OS per physical machine, and you can run multiple operating systems. Okay, and resources often underutilized as the resources are fixed. It maximizes the hardware efficiency by sharing the CPU, RAM, and VMs, means among the VMs. Okay, so what does this mean is, suppose you have a computer and you do not use that computer very much. Okay, so what are the resources present that is only dedicated to your system? Other systems cannot access this one because it is offline and it is dedicated to only this system, right? But in VMs, what happens? In VMs means virtual machines. In virtual machines, what are the resources required? That will be taken dynamically from the internet. Okay, so what is required, that is only taken here, and the remaining ones which are present here, that will be assigned to some other VM, right? So here maximum efficiency is there. None of the resources sit simply. Okay, everyone will be accessing some of the percentage of resources and it is used all the time. So there is maximum resource utilization. None of the resources are wasted there. Isolation, all applications share the same OS. Okay, all of the application will be having the same OS in the traditional system, but here the virtual instances will be isolated from others. So one of the application can be running a Mac, one of the application can be running Windows, one application can be running Linux. Okay, and scalability, adding resources requires new physical machines because one hardware is there. If you want to add another hardware, you have to purchase it, but here you just have to dynamically allocate more resources. You can get a request to more resources and it will be sent to our internet, and you'll be getting more resources in the same systems. Okay, you can go through the other points. The 5 points are more than enough for full marks. Difference between traditional computer and virtualized computer, very important question. Okay, next is the benefits of virtualization. What are the benefits we get? Obviously, as we have discussed now, there are many benefits. We already just saw how many benefits are there. We can run multiple OS and so on. So basically 5 benefits, we can categorize them into better resource utilization, right? And cost savings are there. You need not purchase another new hardware and system for using a Mac, for example. There is everyone dream, right, to use a Mac and Apple products, but if you don't have that much money, you can use a VM which gives all the access to the Mac right in your own system. So that is having cost savings, scalability and flexibility. You can change the VMs according to you, whichever the OS you want to run. And scalability means you can access it, may increase the storage, decrease the storage, and increase the processing based on the requirement. If you are running some game, it is stucking, so what you will do, you'll request for more RAM, and more RAM will be sent to your system via internet, and you will be able to run the game smoothly. So scalability is there. Improved security and isolation. Here security features are more secure than the other one, which is the traditional OS. And disaster recovery is there. This means that the actual data is not stored in your system, the actual data is in the cloud or the internet, and if your system gets blasted, the data can again be taken from the cloud to a new system. So there is a disaster recovery, your data does not get lost. But if it's a traditional computer system, your data will be lost. Okay, so here the architecture, how it is. Okay, this is a traditional computer. Here the hardware stuffs are present, and these hardware stuffs are accessed by the single application. But here what happens, these hardwares are present here, and there is another layer in between, which is virtualization layer. What it does is, it will divide into two different VMs. This is one virtual machine, another virtual machine. So these are accessing the same resources only, but a percentage of it. For example, this is out of 10 hours, this one is used for 2 hours, and this one is used for 8 hours. So 20% of this one will be taken from here, 20% of this one will be taken from here, 20% will be taken from here, 20% will be taken from here. Remaining, which is there, 80% are there in each of these, that will be assigned to this one based on the requirement. And you can run a different OS here and different OS here, because it is separated, right? So this is the architecture of a virtualization. And the layer which you can see here is called as a virtualization layer. It is a software layer that abstracts physical hardware. Abstracts means what? Hides. It will hide the actual resources, and it will just take an image of it, okay, or the imaginary thinking of it. Okay, it will be thinking that it is present here, but it is not present here, it is taken from here. Okay, and it will think that it is a different OS, but it is not different OS nor a different hardware. Everything is getting access from the same one, just that the virtualization layer will hide all of this so that it will not be visible. Okay, so it will think that it is present here only. So that it does the hardware resources, CPU, memory, storage, network, and presents them as a virtual resource to the applications. Okay, it will present it as a virtual resource which is present here only, like that it will think. Okay, but it is not that case. So what is the role of virtualization layer? See, in this module, whatever the role is there, what is benefit is there, whatever disadvantage is there, all are same. Okay, just have to use synonyms and write different words. Okay, so see here, if you go through, I'll make you go through 2 or 3 different advantages, benefits, and challenges, limitations, disadvantages, and roles, so that you'll get to know there are many similarities. You need not remember this, you'll get to know after this module. Okay, so role of virtualization layer. Virtualization layer is what which we discussed here. What is its role? What does it do? It abstracts, means hides the hardware, right? Hardware is present, it will hide it. Isolation means it will take it into two different systems, it is isolated, these are not interconnected. And resource allocation, it will allocate the resources, how much it is required, 20% here or 30% here or whatever. And compatibility, it will allocate the resources such that it will be usable. Okay, compatible. And portability, if you want to take this VM to somewhere else, you can take that as well, it is portable also. So this is the role of virtualization layer. Benefits: efficient use of resources, it is self-explanatory, scalability, improved security, flexibility, and disaster recovery. Okay, next is virtual machine monitor. Now virtualization layer is what? It is just one single layer which will handle all of this. But if you take this thing into a separate system so that you can handle it via a separate system, this separate system is called as virtual machine monitor. Hypervisor is a system that manages all the VMs. There are virtual machines here which you have made, and to manage all of this, instead of a layer, we use another system which just manages all of this. Okay, that is called as VMM, which is virtual machine monitor. So we have discussed about virtualization, virtual machines, and virtual monitor. Now let's discuss what are the different layers present, because it's not straightforward. What you are thinking, it will just be one layer and everything will be handled. No, it will not be handled like that. Okay, there are 5 layers, and this is the very important question from exam point of view. The 5 levels of virtualization implementation. Okay, so there are 5 levels. The first level is the instruction set level, the basic instruction which is there, that handling at which level, that is getting handled at the instruction set level. Second comes the hardware. After the instruction is clarified, you go to the hardware, check which is the hardware used. After that comes the operating system. After that comes the APIs and the library calls, and after that comes the application level. So the different frameworks which are getting used here are given. You can go through it. Okay, I'll be discussing what all is there in each of these. Okay, so let's take each one by one. The first one is instruction set architecture. Okay, what is instruction set architecture level? It primarily focuses on enabling, okay, the execution of instructions. What it does, it executes the instruction 1, instruction 2, instruction 3, go buy eggs, go buy bread, make an omelette. Okay, these are the instructions. So it will execute those instructions written for one architecture on a host machine with a different architecture. So in one architecture it is written, you have to execute in different architecture. Where does the translation happen? The translation happens in this level, which is instruction set architecture level. It will translate the commands and it will be executed in different architecture. So that is the duty of the instruction set architecture level. Firstly, the instruction which is there, that will be available for all the different architectures. Okay, and for that we use the feature emulation. It is the process of mimicking or imitating the behavior of one system in another system. Suppose that you do not have money and you want to buy a Mac, but your parents will say it's not feasible, so you will not buy it. But what you will do, you are intelligent, you know about the cloud computing, so what you'll do, you will emulate a Mac in your system and you will use Mac from there only. Okay, there is a cost saving also. So that thing is called as emulation. Okay, now how does instruction set architecture work? The first step is to translate and generalize the instructions written in one language to carry out in any other language. So suppose I wrote in HTML, it's not HTML. Okay, I'm just taking an example. You wrote in HTML and you want the script to be running in CSS. Okay, so what you will do, you will use the instruction set level architecture features and you will translate it into a general feature, so general language, so that it will be able to run in the what is this, this is the um, what it was, it is the other language. Okay, the generalized, and it will be running in the other language. Okay, so that is the instruction emulation. Second is virtualized instruction set architecture. It does the same thing virtually. Okay, it does the same thing virtually. Okay, whatever I have discussed now, if it's happening virtually, it is called as virtual instruction set architecture. So these are the two ways in which instruction set architecture level works. The key techniques used: code interpretation, get to understand what the code is; dynamic binary translation, translate the instruction into binary code and optimize it. Okay, next is advantages. Advantages is what legacy code support. Legacy means what? Old code. So old code cannot be run on new system. Okay, old code cannot be run on new system. So instruction set architecture level, it will translate into a general language so that it can be used in any system. Okay, cross architecture compatibility can be used between different architectures, and it facilitates hardware upgrade and enables performance in a platform independence. Okay, whatever the instructions are getting run and translated, that is independent of the platform. Any platform can run any platform's instructions. Okay, now the challenges and limitations, it is performance overhead. Okay, to there is not much performance. Okay, and complexity is complex, and scalability is a major issue here. Okay, that was about the first level, instruction set architecture. It will translate the instructions and it will be used in a to execute the operations, whatever it is. Okay, next is the hardware abstraction level. After this comes the hardware. Okay, now the instructions are executed. Now hardware abstraction level abstracts, which is hides and virtualizes the computer's physical resources such as CPU, memory, and input-output devices. Why do we need to hide? We need to hide because otherwise, if you don't hide, it will access the actual hardware and make changes, and none of the other systems can execute. So it will hide it, and it will hide it, and it will just give a percentage of it to make it think that it is an independent thing, and it will do the same for the other ones also. So what is the advantage here is that you'll be able to execute different systems simultaneously. So this is the task of hardware abstraction. It will hide the hardware and give a fake hardware to the guest OSs. Okay, what are the key features? Bare metal hypervisor. It operates directly on the hardware, so none of the other layers are in between. And use resource utilization is happening here. It improves the hardware utilization because now all the hardwares will be utilized efficiently. And isolation is there because the other OS will not know which OS is getting executed parallelly. What are the advantages? Again, the same thing: high performance, scalability, fault isolation, and versatility. Means different OS can be run in the same system. Okay, after that comes the operating system level. Here what happens, it operates in different OSs. Okay, it creates containers that allow multiple OS to be run on single hardware. Okay, one hardware is there, multiple OS are getting run. How it happens? It happens by another layer inside the virtualization layer called as operating system level. So what are the key features? Single OS kernel is there. A single OS will be handling all the different OSs. Okay, and isolated environment is there. The environments are isolated, and again the same thing, efficient resource utilization. Advantage: it is lightweight, it will not use much resources, it will run faster, high performance is there, scalability is there, isolation is there, and ease of deployment. You can easily deploy. Till now you have got to know, right, what are these are the same things. Okay, in advantage, disadvantage of all the layers, same things are there. Okay, and the disadvantage is it's only related to single OS can handle multiple OS. Okay, only single OS can handle. If it was multiple OS can handle, then it will be more better, but it will become more complex. So only single OS is there. That is one disadvantage. Second is weaker isolation. Isolation is very weaker there. Okay, and the compatibility issues is there. Sometimes it will have compatibility issues for running one OS in different kind of OS, because there will be dependencies. Okay, fourth level after the OS level is the library support level. It is done at API level. The virtualization is done. So what are the key features? It uses the API hooks or libraries. The libraries is nothing but codes written already, so that we can directly call it and use it instead of writing the same code again. And control communication is there. That is an advantage. And application specific virtualization is there. Application is there, specifically you want to virtualize it with respect to that application, so that is possible in the library support level. Now how it works: applications are written to use standard library calls for their functionality, such as file access, networking, or graphics. Whatever the task, okay, I repeat, whatever the task you need to perform, that will be already written which library you have to use. Okay, and library level virtualization intercepts these API calls using API hooks, okay, and replaces the original functionality with emulated or redirected behavior. So there is an original functionality, we are implementing it, but it is not that efficient. So use a library so that more efficient call will be made and it will be more efficient. Okay, so that is the how the library level works. The last level is the user application level, the level which we are concerned with and we directly interact with. Okay, it refers to the virtualization of individual applications. And the key features: high level language in virtual machines, because whatever we see in the virtual machine, that is a high level language, the end thing which we see. Okay, it's not the binary or the machine level language. Second is application isolation and sandboxing. Okay, you can have different instances of the same app at the same time. For example, if you opened a notepad but your system is very useless, okay, so notepad did not open, you became angry, you click notepad 100 times, after 1 minute 100 notepad will open. That is what different applications getting opened, different instances, and it is isolated. Each notepad will not know what the other notepad is doing. Okay, and it is sandboxing. Sandboxing means creating an instance of it of the main application in different instances. Okay, and application streaming, you will be streaming the application and using it at the lifetime. Okay, again, advantage, disadvantage: cross platform compatibility, improved security, simplified deployment, resource efficiency, portability. Disadvantages include performance overhead, limited scope, and compatibility challenges. Okay, now, an example for virtualization is the Linux platform. Okay, OpenV2. Okay, OpenV2 is an open source container-based virtualization for Linux-based platform. It creates virtual private servers. Okay, virtual private servers it will create, so they act like an independent Linux server, so that Linux things can be performed virtually. The key features: isolation, resource management, and checkpointing and live migration. We'll be discussing live migration in the upcoming topic. Advantage is that it is efficient and quick migration is possible, but the processing is delayed here. Okay, that is about the Linux virtualization. Now that was about the OS level, operating system, which is Linux. Now if you want to virtualize it at the library level, few of the APIs will be used. First one is WABI, which is converting the Windows calls to Solaris system calls. You have Windows but you want to run on Solaris. What you will do, you will convert it using the WABI. Okay. Second one is LXRun. Again, it's the same thing. It is enabling Linux application to run on Unix. Wine is used to run Windows on Unix. Visual Main Win is used to run the Visual Studio on the Unix system. And vCUDA is nothing but it will help to run the GPU. Okay, if you have used the Google Colab, in Google Colab at the top you can select the option, right, CPU or GPU. So the GPU which is getting used from there, it is using the vCUDA in the background. Okay, so you can use the GPU without having the GPU in your system. So vCUDA for the virtualization of general purpose GPUs. Okay, it is a virtualization solution designed to enable CUDA applications to run on a guest operating system by virtualizing the CUDA library. And key features: we can run the GPU task directly on the system without having a GPU card installed. It follows the client server architecture. It does the abstraction. It hides how it is happening. We are just able to see. We are able to use. That's it. It handles the memory flow execution and it stores the flow for the next time. And vCUDA library and the stub handles the API calls. What handles the API calls? Library and the stub. Okay, so here's the architecture. Here we have the stub and here we have the library. So these are connected via the device driver to the main device, and VMM will hide all of this and we'll be able to see a library here and we'll be able to use it at the user's end. Okay, guest OS. The host OS is like a server and guest OS is like a client. Okay, we are the guest OS and the host OS is nothing but the actual OS which is present. Okay, now Moving on to the second topic. The first topic was related to the virtualization levels. Second is the virtualization structures, tools, and mechanisms. So in this topic, we will be discussing what are the structures used, what are the tools used, and what are the mechanisms or the operations we'll be using for virtualization. Okay. Basically, the VM is divided into three types of architectures: hypervisor, para-virtualization, host-based virtualization. Hypervisor means what? It operates directly on the hardware. Para-virtualization, it is a modified version in the guest OS side. Means from our side, okay, we are getting a resource and that is a bit modified. Okay, and modified version is a better one in this case. Okay, so the third one is host-based. It runs on top of the host. Host means server. In the server, it is running. Okay, so these are the three classes of VM architecture. And why do we need this? It is crucial because to translate real hardware into virtual hardware, we have to perform operations on virtual hardware. Okay, we cannot access on real hardware, otherwise only one operating system will be having. So therefore we need to have a translation, and translation who does? Virtualization layer. Now hypervisor or Zen architecture. Okay, what is hypervisor? Hypervisor, it is acting as an intermediate between the hardware and the OS. Okay, operating system is there, hardware is there. In between what we have? The VMM or the hypervisor. Okay, what it does? It facilitates the actions between these two. It facilitates the creation of virtual resources that guest OS and the application can utilize. Okay, there are two types: microkernel and monolithic. Microkernel is related to the only essential and unchanging functionalities. Monolithic integrates all functionalities. Key features: supports virtualized access to physical hardware through hypercalls. Okay, hypercall means what? Hypercall means this is the virtual environment, this is the actual environment, and if you want to access something from here, you will be calling it, and that call is called as a hypercall because it's happening through the hypervisor. Okay, in the implementation of this blueprint is called as Zen architecture. Okay, Zen architecture is the implementation of microkernel architecture. As I discussed, microkernel will be having only essential and unchanging functionality. So let's have a look. In the Zen architecture, the components include hypervisor, kernel, and application. These are the applications, and this is the kernel, and the hypervisor is in between. Okay, so these are the hardware devices. It has to be accessed by the different applications. Suppose that this is your friend, this is you, this is your enemy. So three people are using the same system and using the same hardware devices. How the distribution should happen? It should happen based on the functionalities and the policies defined by the Zen. So some will be given here, some will be given here, and some will be given here. So three different people will be using the three different OSs based on the same hardware, and that middle thing is done by the Zen, which is a hypervisor. Got the point? The example and the definition. Next is the host based virtualization. But before host based virtualization, you need to understand what is binary translation. See, all the commands which is there in the machine level means the basic at the hardware level, those are ones and zeros. Okay, but the computers cannot understand ones and zeros if you use it virtually. So there has to be a translation happen so that it will be translated to some execution commands, so the commands will be run. Okay, how does that happen? Two ways. First is full virtualization, second is host based virtualization. If you go for the full virtualization, here it allows the guest OS to run without any modification using binary translation. So basically, if the hardware is here, the binary translation will happen and the guest OS will be able to use these things. That is the full virtualization. Second is the host based virtualization. It manages the hardware, but it is difficult because there can be different architectures. Okay, host based we can use it, but it will be different architectures is there. It may work, it may not work. Okay, so this is the architecture here. This is the hardware given here, and these are the apps which is getting used on top of VMM. Third one is the para virtualization. It replaces the privileged instructions with hypercalls. As I discussed, hypercall is a call made between the VMM and the original system, and whichever is the privileged instruction, important instruction, that will be replaced with hypercalls. And it improves performance but has some limitations. So what are the limitations? Compatibility and portability issues. Okay, it is not always compatible, and portability issues are also there. High maintenance cost is there, and variable performance gains is there. Sometimes it is giving better performance, sometimes it is giving worse performance. Okay, so this is the architecture, and the architecture is very simple here. This is the hardware. Here is the hypervisor. On top of hypervisor, we have para virtualization. Okay, hypervisor will always be there. On top of this para virtualization, there's some modification will happen at this point, and we'll be able to use those modified applications. Okay, that is called as the hypervisor. Here also it's the same thing. Virtualization layer is here, and the user apps are given here. Okay, there will be a different rings formed. Okay, based on how many user applications are there. Now, para virtualization with compiler support. Okay, if you're using the para virtualization and using a compiler support means it helps in the translation and modification. Whatever the modification we talked about which makes it more better, that will be there. Okay, hypercalls will be there, intelligent compiler will be there. It will be optimizing the instructions and performing 3 instructions in one single instruction, like that kind of changes. Okay, and improved efficiency is there because it will take less time. Limitation is that it cannot directly run on physical hardware. There is another layer of para virtualization required. Okay, now due to inefficiency of binary translation, if we do basically without any optimization, it will be taking a lot of time. So we want something which will be not taking a lot of time, so we use the solutions. So solutions will be used by Zen, KVM, and VMware ESX. Zen we discussed how it does, right, in the previous topic. KVM will be discussing, VMware ESX will be discussing, to make the translation more faster. Okay, so KVM, kernel based virtual machine, what it does, it is a Linux based para virtualization system. It leverages Linux existing memory management and scheduling. Okay, so what it will do, it will do the para virtualization, which means behind the guest OS at the last layer, it will do some modification. Okay, and how it does, it will leverage the existing memory management and scheduling of the Linux, and it supports unmodified guest OSs including Windows, Linux, and Solaris. Also, it supports, if you don't want to modify anything, it can support that unmodified thing as well. This is about KVM. Next one was VMware ES6. What is VMware ES6? It is a bare metal hypervisor. Bare metal means what? It directly operates on the hardware. Here, para virtualization thing is not restricting it. It will directly access the hardware with the features of para virtualization. It is designed for x86 architecture. Okay. Key components: virtualization layer is present. Resource manager. It will manage the resources, and hardware interface components are there. It will handle the hardware interface components. And service console is there. Whatever is happening, you'll be able to see in the console, and you can handle the commands using the console itself. Okay, and para virtualization in VMware ESX works by interacting directly with the hardware, bypassing the OS. Here OS is not required. Okay, remember again, VMware ES6 hardware is directly getting interacted and OS is not required. So the architecture is given here. This is the VM kernel, and directly hardware is getting accessed by the VM kernel without having an OS in between. Okay, as you can see, there is no OS in between, right? There is a virtualization layer and directly accessing with the hardware. Okay, so that was about the second topic, which is about the virtualization and para virtualization and different kinds of features in that. Okay, so let's discuss the third topic, which is virtualization in the CPU, memory, and the IO devices. Okay, so how does virtualization happen in the CPU, memory, and IO devices? Okay, we'll be discussing each one by one. The first one is the CPU. Before that, we need to understand what is the requirement to virtualize each of these aspects. Okay, to virtualize CPU, virtualize memory, virtualize IO devices, what are the requirements? So hardware support for virtualization. Execution is divided into two modes. Okay, what are the hardware required? Okay, means what is the sugar required, what is the coffee required to make a coffee. The ingredients required to do the virtualization, it is divided into two parts: user mode and supervisor mode. User mode is the ones which we use, and whatever we want to do, it will do. Supervisor mode runs automatically behind the computer, and it is handled by the kernel. Okay, two modes are there. For these two modes, we need to handle both of these. Okay, so several solutions leverage hardware for support for the virtualization: VMware Workstation, Zen Hypervisor, and KVM. So these three things use the hardware support for the virtualization. Okay, now hardware support, like an example for the Intel processor. As you can see in this diagram, the top layer which you can see, it is all the virtual machines, and in between we have the virtualization layer, and this is accessing the hardware. Okay, so as you can see, this is cleanly categorized and organized. Here we have the VMs. After that, we have the virtualization layer, and in the virtualization layer we have VTX and VTI, which helps in processing and performing the tasks of accessing the data from the hardware and the internal system. Okay, using the network and the storage. And if you want to expand it, you can also use VTD and VTC. Okay, so VTX and VTI provides privileged instruction execution, which is the important execution happening. It will access those instructions and execute it on priority. Second is for IO virtualization, input output virtualization. The Intel provides VTC and VTD. Okay, as you can see here, this is VTC and VTD. It provides the IO virtualization, means the input output can be accessed from elsewhere. Okay, so we have understood what is the virtualization's requirements. Okay, now let's discuss the CPU virtualization. CPU does what? It does the calculations and arithmetic operations. VM replicates real computer system. It executes privileged instructions and critical instructions. Okay, whatever is the happening in the real computer, that will be happening in the virtual computer as well. Okay, so it will be having critical instructions, which means important instructions, like for example privileged instructions, control sensitive instructions, and behavior sensitive instructions. Okay, this has to be handled automatically. How does it happen? RISC CPUs are naturally virtualizable. There are two types of CPUs, RISC and x86. Okay, RISC are the ones which can be virtualized, but x86 cannot be virtualized. To virtualize this, we'll be using some features. Okay, so in para virtualized system, the system call triggers ATH interrupt in the OS. Okay, ATH is called and also calls the 82H in the hypervisor, so that the hypervisor processes the call before returning to the guest OS. So these two calls are made so that the operation becomes more successful and efficient. Okay, and to simplify the virtualization, Intel and IMO introduced hardware extensions. Okay, if there is more hardware, more things will be performed efficiently. Got the point? It adds new privileged mode, which is the ring 1. Okay, hypervisor runs at ring 1 and guest OS runs at ring 0. So there are different rings or different layers. Here is the guest OS will run, host OS will run, and here the user mode will be there. Okay, all privileged instructions are trapped in hypervisor because it has to be executed on priority, so hypervisor will be executing them. Okay, so Intel hardware support for CPU virtualization. Virtualizing x86 processors, the Intel's hardware, what it does, it will virtualize x86, which was not previously virtualizable, right? So it will do some hardware modifications so that x86 processors can be virtualized, and it induces VMX root mode. Okay, what it does, it adds instruction to start and stop VMs and allocate pages in the memory management. If you have a look at the performance considerations, it is having high efficiency, but switching between the hypervisor and guest OS causes overhead. Okay, so it is not easy to switch between these two frequently. Okay, and this is the diagram given. Okay, here we have the main CPUs, and in between we have the root module which handles both the CPUs and the virtual machines. Okay, next is the memory virtualization. Now we had discussed the CPU virtualization. How can CPU be virtualized? How do we virtualize memory? There are two methods. Okay, there are two stages. Guest OS is the one which we are using, and from there the mapping comes from the virtual memory to the physical memory. And from the VMM, what happens is the physical memory gets mapped to the machine memory. Okay, that two things will be there: physical memory to machine memory, and guest OS virtual memory to physical memory. Okay, now, to ensure that this works, memory management unit and translation look aside buffer will be used to help in memory management. Okay, and shadow page table, SPT, and nested page table are used for handling memory allocation and access. To allocate the memory and access the memory, which two things are used? Shadow page table and nested page table. Okay, now Intel has introduced extended page table for memory virtualization. Now, what is the problem? Problem is shadow page table were inefficient as they required frequent context switches, and as I told you, context switches will require more resources and it is not easy. So introduce uses extended page table. What it does is it will hardware assess the memory, works with the virtual processor ID VPID to solve the problem. Okay, it uses 4-layer page table hierarchy. So in the 4-layer page table hierarchy, the context switching issue vanishes. Okay, and improvement is it increases the size of the table so it becomes more enhanced, and impact is the faster it is faster and removes multiple dependencies. So this is the diagram for it. Okay, extended page table. Next, third one is the IO virtualization, input output virtualization. It allows us to access input output devices virtually. Okay, there are actually there are three methods, but these are categorized into five methods. Okay, means these two are one method, these two are one method, like that. Okay, so full device emulation. If you want to emulate the full device, okay, like the whole device will come, you will perform input output operation inside the system by using the emulation. That is the first method. Second is para virtualization. Here we'll be having front end and back end handled. Okay, so that front end will be handled independently and back end will be handled independently, and whichever we want to access we'll be able to access. Third one is direct IO virtualization. You'll be virtualizing the IO directly, or you will be using a hardware, or you will be using a virtualization to virtualize the input output. Okay, and one of the example is VM workstation for IO virtualization. So VM workstation runs on the host OS. Okay, and in that we have the VM app, which is the application layer. It runs as an application inside the host OS and manages the VM operations. Okay, and what is VM driver? It is the host OS driver. It acts as a bridge between VM app and VMM. Okay, so the VM app is there and VMM is there. In between them, what is the connection in between them? It is the VM driver. Okay, it transfers the control between VMM and host OS. Virtual machine monitor runs directly on the hardware, and processor executes in two states: host world and VMM world. If it runs on the physical device, it is host world. If it runs on the virtual device, it is VMM world. Advantages, disadvantages: broad compatibility, runs as host application, leverages host OS, and disadvantages is that there is some overhead in it, performance is not that good, and it is slower. Okay, and this is the diagram for it. Next is the virtualization in multi-core processor. One core means single core, multi-core means if multiple cores are there. Okay, it is not straightforward. It has complexities to virtualize multiple cores. The challenges are parallelism and programming models are not straightforward. Okay, to do it the things parallelly in multi-core, it is not straightforward. Task scheduling and resource management needs to be handled efficiently, and dynamic heterogeneity should be there. To address these challenges, we are introducing the virtual processor cores, VCPUs, which abstract low-level hardware management. Okay, low level hardware management is the actual ones, actual hardwares are there. It will abstract it, means it will hide it, so that you'll be able to just access the outer features of it. Okay, and virtual hierarchies optimize the working of it. Okay, so this is the physical course and these are the virtual course, and the software works on the virtual course. Okay, now virtual clusters and resource management is the fourth topic. What is virtual cluster? Cluster means what? A group. Virtual cluster means a group of clusters. I mean, virtual cluster means a group of virtual VMs. Okay, formed as a cluster. So these are the physical clusters are there, and these are connected with the virtual machines, and the virtual machine themselves form a cluster. Okay, and this is the diagram. Live VM migration and performance effects. Why do we need to perform the VM migration? Suppose that this is a VMM which handles all the VMs. Okay, if this fails, none of the VM will be getting the resources and none of them will work. So if one of the VMM fails, we have to migrate it to another VMM. To do the migration, there are few steps. Before that, there are different kinds of approaches. First is the guest based manager, which in which the cluster manager runs inside the guest OS, means the VMM is present inside the guest OS. Second is host based manager, which runs on the host OS. Third is the independent manager. Both guest and host have separate clusters, and integrated cluster means both will be having one single in the virtual and physical resources. Okay, these are the different approaches are there. Now, no matter which approach you are using, the steps are same. To migrate the VM from one system to another system, the first step is to start the migration. Identify the VM and the destination host, then start it. Transfer the memory, suspend and final copy. Okay, means transfer should be paused whenever it should be it has the last memory portion to be transferred, and the CPU will be there and network states will be there. So finally there will be a suspension between the final copy. Commit and activate. Destination host should load the VM and activate the VM. Redirect the network and clean up. Now since it is a new VM, all the network should be redirected to the new VM from the old VM. Old VM it should be removed. So these are the steps for the live migration. And performance effects, total downtime is only 165 milliseconds. To do the migration, you might think it will take 1 day or 2 days. No, it will not. It will just take 165 milliseconds. And this is the diagrammatic representation of the same pre-migration step. Then we'll reserve the target host. Iterative p-copy will copy and stop, and then we'll commit it, and then we'll activate it. Now, while migration, three main things are to be taken into consideration: memory migration, file system migration, and network migration. To enhance memory migration, we'll be using tree-based file structure. What it will do, it will just copy and paste the relevant parts. Next is file system migration. It will have the global access so that every file can be accessed and only the difference between old and new location is transferred. Third is network migration. Detect new VM location and reroute the traffic automatically. And live VM migration techniques. Four techniques are there. Pre-copy approach. It transfers all the memory pages first. Second is checkpoint recovery and trace replay. If there is any issue happen, we will be going back to the checkpoint. Post copy approach transfers all the memory pages once but has higher downtime. And fourth one is memory compression. You'll be compressing the data into smaller part and then you will be transferring it. Okay. Next is the dynamic deployment of virtual clusters. To dynamically deploy, we use the virtual clusters. Okay, to change size, move, adapt. So it is not always the case that all the allocated resources will be used. So if there is any requirement which is not used, that percentage will be taken from each of these clusters. That is called as dynamic deployment of virtual clusters. This helps in resource management, improved performance, and cost savings. Okay, so few examples are cluster on demand, dynamically allocate servers to multiple vClusters, cellular disco, it deploy a virtual cluster on shared memory, and Violin, it improves the performance through dynamic adaptation, and Graal in RIA, which is helping in the parallel algorithms execution. Okay. Last topic is virtualization for data center automation. Now, what is data center automation? It means huge volumes of hardware, software, and database resources in these database centers to be allocated dynamically to millions of internet users simultaneously with guaranteed quality of service and cost effectiveness. That means that there are millions of users. Okay, 1 million users, suppose there are in the internet, and there are resources. Now, all of these resources has to be allocated to the people who need it. And it's not always the case that whoever needs it will use it fully. Whichever the part the person does not use, that part needs to be allocated to the other person who wants to use it. Okay, So that is called as virtualization for data center automation. First thing is server consolidation in data centers. That means some servers work 24/7 and others do not work 24/7, because in the night time office will be shut down, okay, the companies. So nighttime computers will not be getting used. So the each computer will be having some resources allocated. These are not used in night time, but when there is night in India, there is a day in USA. So these things is not used during the daytime in USA. So if it is used dynamically, means this will be not simply sitting, they will be having maximum utilization, right? To ensure peak performance, the servers are allocated top configuration. So each server will have a lot of memory spaces which is not actually used all the time. So they have to be allocated to different people who will be using it. So that cloud does, okay, that is called as the server consolidation. Next one is virtual storage management. To manage the virtual storage, we will have to manage the VM images and application data, okay, and the storage gets lagged in most of the time, which is the main bottleneck of VM deployment. The storage gets lagged in between, okay, there is some storage previous version, and that will be seen after a long amount of time. Virtualization layer is inserted between hardware and traditional operating system that complicates storage operations. Hardware software between that VMM is present, it will complicate the operations, and in VMs this becomes very difficult to handle in virtual machines. To solve this problem, parallax is used. What is parallax? Parallax means it is a distributed storage system for virtualized environments. Okay, what does that mean? It will have content addressable storage (CAS), which is used to reduce total size of VM images. It will compress it. Okay, means more storage is there, it will put it in a small space. Okay, and this is a diagram for it. This is the block device, and these are the different VMs present, and this will be interconnected. Okay, so in this way, the parallax handles the issues which VMs was facing. So it runs as user level application in the storage appliance VM. It provides wide virtual disk images. So more images space will be there, so that VMs will be having easily they can transfer it. And VDI is core, the core abstraction provided by the parallax. Okay, so they'll do the abstraction as well, okay. And cloud OS for virtualized data centers. So the data centers must be virtualized to serve as data centers, right? Without virtualization, data centers will be present at just one location, they cannot be used by different people. So we need to virtualize it, and to virtualize it there are few different managers, OS platforms and licenses like Nimbus, Eucalyptus, Open Nebula and vSphere 4. Okay, so these are the information given here for each of these. They have different kinds of features also, okay, and which interfaces they are using, what are the hypervisors used, what are the API languages used, okay, what are the resources being virtualized and web link. All these things are given here, okay. So these are the cloud deployments happening in the virtualized environments. Last one is the trust management in virtualized data centers. Now suppose that VMM is handling all the devices. If the hacker hacks VMM, all the access to these VMs will be gone. So how to ensure that the hacker will not hack, how to make it more secure? For that we'll be using few techniques. First is intrusion detection system, IDS. It monitors the actions of intruder and analyzes if it is the hacker or not. So they will be training the model for detecting the hacks. Whenever a hacker comes, he will try to access a large amount of data. It will do the actions in a specific manner which normal people don't do in that manner, right? So that will be detected, it's an intruder, okay. So next one is policy engine and module. There will be specific policies implemented to monitor guest OS, okay. So based on that policy we can detect if it's a hacker or not. Third one is very interesting, honeypots and honey nets. These simulate and provide a fake system to attract the hackers. So what happens? Hacker will think the hacker has hacked the system, but what? Hacker is hacking a fake system, okay, and the people who are behind it, they are looking how the hacker is hacking the fake system and laughing at the hacker, okay. So hacker will be thinking he's hacking, but he's hacking a fake system, okay. The hacker's insult will happen. And monitor their actions, they will be monitoring his actions and keeping the original system protected. Hacker will be hacking fake system and the original system will be safe somewhere else. So this is the third method to ensure the hacking not happens, and if it happens, it gets detected. That's all for this video. If you found this video helpful, please do like and subscribe, and thank you so much for watching. I'll see you in the next one.